I am Leszek Maciaszek, and I represent Wrocław University of Economics and Business and Macquarie University, Sydney. And I have this great pleasure to be chairing the session of Schahram. But you know, some people do not need introduction. Martin has introduced some politics in our conference because he loves America. So I was thinking, what if I were to chair a keynote speech by Donald Trump? I would not read his CV, right? So I would just say President Donald Trump. So now I can say Professor Schahram Dustdar, and that's everything what you need to know, because you know everything else about him. In fact, it would be an insult to computing community, which we represent here, if I were to introduce here or read a CV of editor-in-chief of a computing journal. So I am not going to be doing this. Schahram is an excellent scientist, but most of all, he is a very positive person. He is really contactable, he is humble, and he is also very friendly. And talking about friendship, you perhaps know that in C++ and in C# there is a notion of friendship. So an object like Leszek can declare an object like Schahram to be a friend. The problem with his friendship in C++ is that it is not reciprocal. So now he has a problem, because he has to say that he loves me, because otherwise he wouldn't be making me a friend. I would like to be his friend. So yes, so this way I am putting you back to programming languages, not just to large language models. Jokes aside, research-wise, Schahram is simply ahead of others. To me, he is a kind of visionary. And today, Schahram will share with us his dreams and vision about distributed intelligence. Please, Schahram. Okay, you have your mic, yeah?
Yeah, I can take this. Thank you very much, Leszek. Yes, I do love you. Yes, yes. Well, that was an awesome introduction. The first one I got like this is very unusual. Thank you so much. So, and thanks for the invitation. It's really nice to be here. So in this talk, I will speak to active inference and distributed intelligence in the computing continuum. So there are a lot of different words you might not be fully aware, because we are from different communities. So I will try to unpack everything. And it is right, Leszek said, it's kind of a visionary, because I think that a keynote should be kind of looking forward and not looking backward necessarily. And the first thing to unpack here is, what is a computing continuum? The computing continuum is a fabric of computational tiers. It is basically speaking to the integration of these different computational tiers for different types of systems that we have today, like healthcare systems, autonomous vehicles, and things like this. And if you've observed the last 15 or so years, we can see that the typical systems that we are building, even we think that they are distributed, in reality, conceptually, they are pretty much centralized. So we are building systems which are operating on the cloud, and that's basically what we do. Even though the system has different computational tiers, the majority of the action happens on the cloud. So and the idea now here is to actually see all of these different computational parts of the resources infrastructure as one computing continuum. So the question then becomes, what do we actually do with the IoT world? What do we do with the edge? What do we do with the fog? And what do we do with the cloud? And in the future, maybe also include quantum computing and things like this. So currently, we can say that we have a limited visibility over the system performance, over the quality of quality of service and quality of data, because of this fact that they are treated in isolation. Two major problems that come here into the foreground in this space is that they are multi-proprietary. This means that we have different infrastructure ownerships of different people. So the stakeholders, they do have their own global interests, and though we have local requirements of the infrastructure. And we do not have a clear understanding of the relationship between these different requirements, in the service level objectives, for example. When the system is executing, the propagation of trouble, we cannot really pinpoint it very well because of the nature of how the systems are being created. The second issue is that they are geographically distributed. So the challenge comes that we are not really able to do centralized governance by this nature of this distribution of the centralization. So now the goal for me personally is to bring intelligence or decentralized governance into these types of systems which are running across this computing continuum. That is the overall goal here. When we look at governance or intelligence, here we actually want to include sensors, edge, fog, and cloud, and it becomes obvious that we cannot simply react to with a centralized management in place. We need to also have some form of prediction overall in the system built in. This is kind of my first claim, a sign of intelligence when we have more predictive capabilities inside the system parts. So how can we bring this intelligence? There are different types of lenses, as I call it here, for predictions, for regulating the predictions. One is a biological lens. I'm a big fan of this, and I will work more on the biological metaphors here. And I think that as humans, for example, we have excellent anticipating change capabilities. So we have these two principles, as you are aware, homeostasis, allostasis. So one is reactive, one is predictive. And as it is called, the free energy principle in the human nature, we try to minimize prediction error. So this is why we are kind of also, to a degree, stubborn. We try to minimize the changes that we have to create new models in our worldview. So we always try to predict what is going on. And we have different levels of how we do these predictions. And I think this is actually pretty worth to mimic in the world of systems. And typically this is not something that we do. But there are also other lenses, like the physical lens, where with the fluctuation dissipation theory, for example, which has a very similar spirit in this. We try to create an alignment in the equilibrium. Basically, we compare expected versus the observed responses. So the term predictive equilibrium, which I like to use, is that we try to create an alignment between these two. So in other words, we would like to be right most of the time, quite precisely. So this is a basis for what Nassim Taleb calls antifragility, which I think is a very interesting term. Antifragility is, in a sense, the advanced version of resilience. So we try to become anti-fragile as a human. Now I'm using the biological lens. We become anti-fragile when we are stress tested a lot. That can be physical only by breaking down muscles and then we become more muscular, but it can also be seen as a traumatic experience. If we have traumatic experience and we grow from that and learn, we become better versions of ourselves. The downside is if that doesn't help, we might actually go down and break down, right? So then we are not really anti-fragile. So, but this is a goal that we try to achieve. And whenever we look into this world of probabilities, of course, we hit with the Bayesian theorem, which essentially is about updating the beliefs that we hold, right? So before we have a so-called prior, we have a belief about seeing the world, seeing the data. We observe something, we assign a certain likelihood of the probability of what is happening. Then we have some evidence, and then we have some updated belief after the observation, right? And this is essentially a mechanistic view of how things are done by Bayes' theorem. So for example, if we say, okay, today is a 30% chance of rain, and there is a certain likelihood then that if it's raining, the grass is wet. There are also other alternatives. Somebody might, sprinkle the grass, and we observe that the grass is wet. We then basically posteriorly, we think, what is the probability that this was caused by rain, etc. And by using this, we constantly operate in the world, right? So we go around and we assign probability paths to probabilities to the different events that are occurring. Now, the term variational free energy is a measurement how well an approximate posterior matches the true posterior. This is quite important for our world, what we are talking about. So what you see here is I'm introducing to you a couple of terms that are important in this, and we try to fit the data so that we are able to understand why we are changing our beliefs. In the world of humans, this is basically an understanding of why we are doing certain things, and we can point to that set of events, and then therefore we are able to know why we're changing these beliefs. So this is important for us, because if we lack the capability of reflection, of going meta, we basically are just operating on the instance level. We are not making progress. Now, what is interesting in the world of biology is that we operate on the free energy principle. This means we are always trying to minimize that. We are trying to minimize the surprise. We actually don't really like surprise. So we have to artificially introduce it in many times, right? And then create a sequence of actions so that we evaluate our policies, meaning what we have done is that leading to a certain outcome that we had in mind. And that outcome is measured in the Kullback-Leibler divergence, which measures the dissimilarity between two probability distributions. If it is 0, basically we have a perfect match. If not, we know that we are different, right? And in the world of active inference, this is a framework from neuroscience, is researching exactly that. It is trying to understand better how the human actually learns. And what is fascinating to me is that the way that humans learn is so different from how machines learn, right? And we will use this also for understanding how learning occurs in the world of systems. And there are different types of examples here. I don't go into this, but it's basically a distance metric between expected and observed behavior. And this essentially is a tool for us for antifragility. It helps us to build systems which go beyond typical resilience. They actually become stronger when they are challenged. Like in the world of humans, if we are challenged and we master it well, we actually improve and become better. But in the world of systems, we actually typically don't think like this. We have a fixed set of requirements, and we are pretty happy if they already fulfill that. We don't think that if they can actually become better. So this is the long-term, let's say, vision, if it is possible to create anti-fragile systems which improve by stress. And we want systems to be in an equilibrium, but equilibrium not in a sense that it is stable, that is always the same. It's not a point. It's more like a space inside a certain space in equilibrium, similar to the biological equilibrium that we are. So we try to be in equilibrium, as you remember the biological lens that we have. So this is what we try to do. We try to create mechanisms to have this predictive equilibrium in real action. So in this whole computing continuum that I'm talking about, the edge, the fog, and the cloud. Okay? Now, I'm following the biological metaphor. So in human biology, the human body is comprised of a series of complex systems. We are all familiar with it. So we have the skeletal system, we have the nervous system, the cardiovascular system, and those determine the infrastructure of our bodies, right? But there is more. We have the lymphatic system, the endocrine system, and they are for regulation, right? Now, the nervous system is a very interesting part because it is composed of the brain, the cranial nerves, etc., and it has a big computational infrastructure at its disposal, and that is the brain, the mother of all computing metaphors, right? The brain has around 86 billion neurons, and therefore it is a computer, a computing resource, so to speak. But my argument here is that also in the human, which is a role model for complexity, not everything is done in the brain. We have also the cardiovascular system with the heart at its center, and the heart has also 40,000 neurons. So it is also a computational device, if you like. And there is even more. We have the gut. When we say we have a gut feeling, it is because we have 100 million neurons sensing the world around and making sense of it. So as a human, we are basically a computing continuum as well. We have 3 computational centers, the brain, the heart, and the gut, in constant communications with message exchange, biochemistry, and all the rest of it. So, and I use this as a metaphor also for the computing continuum. I'm saying that essentially similar to the human body, in the computing continuum, we have IoT sensors, we have edge infrastructures, and we have cloud infrastructure. And the exercise now is for us to create an ecosystem for the computing continuum, which includes all 3 aspects at the same time. It is not that one is more important than the other, but the question is how well balanced is this overall infrastructure. So now you basically get the general idea where this is going. But there are also other parts, of course, which are extremely important, which I will not speak about, is like the security system of the human body, the immune system that we have, what is actually happening there. So my talk is mostly focusing on the infrastructure perspective. So the question, how can we ensure that these fundamental infrastructure level things are actually working in the world of systems, which is kind of unusual. We have never thought about this typically because we are optimizing our systems for a particular infrastructure, namely the cloud in most cases, that we are building them. So learning and the idea of what are the mechanisms of learning are actually really key ingredients for this, because the way that we learn from, let's say, traditional machine learning vis-a-vis how we should learn in such a distributed, decentralized scenario, I would claim is probably very different. And I think it is more similar to the way that humans need to learn versus how we do machine learning nowadays. That's my claim. So we look more deeply into the world of biology and try to mimic that. And that is what we came up with, and I'm going to talk about this in the next minutes. So learning and these different concepts related to this are key, but as I said, other aspects like security, etc., are also equally important. Now, when we look at the human body, we always self-regulate, as I was saying in the beginning. We do that by temperature, blood pressure, and things like this. And all healing in the body is done by the body. It is really interesting to me when I studied this and I see that actually medicine is not healing. Never. Medicine doesn't bring healing. It just triggers some things. Some values go up, some values go down, and that kind of kicks the healing process in the body. That's always what is happening. And that I find is very interesting. So it's always a self-healing. You just amplify it. And the problem is that we are not really able to see what is going on inside the body. So we just regulate it, but we don't know why. So it's not possible for us to say, I don't feel very well because I think my kidney is not really functioning in the filter function on my liver. I don't know that, right? I can't read. Maybe I'm sweating or something, but I don't know what's going on inside. And this is the reason that is leading to a lot of problems for humans. And similar problem occurs in the world of systems too. When things go wrong, we don't really know what's going on and why. And my goal is to understand better how we can find mechanisms to deal with this so that we are not just on the symptom level, as we are in medicine today in most cases, that we just say, okay, this is not functioning, and we try to patch it here and there. But we go more to the root causes of the problems in this computing continuum. And the first thing I discovered some 12 or so years ago is the principle of elasticity or resilience. And I thought that this is a very important ingredient of everything that goes on in resilience. And elasticity is a principle that we find in biology, but also in material science and physics. It is a property when we put force on a material, it deforms. If we take away that form, it goes back to its initial form, right? So this seems to be a very fundamental property. And of course, like 15 years ago, when the cloud came, everybody was talking about elasticity. So this term became also popular in the world of computer science. But I always was finding that it's a little bit different to what I had in mind, really, because mostly in reality, people were talking about scalability. It's a more sexy word for scalability. And I thought, actually, I would like to see it in a little bit different way. It would be more in a multidimensional space. So, for example, elasticity, as I would interpret it, is more than just scalability. It considers resource elasticity, but at the same time, it also considers quality elasticity, so the quality of the data input and output, and at the same time also considers cost elasticity. So in other words, when we build systems, they take into consideration all three dimensions at the same time. And this is something that I was saying that is kind of new. In the past, we were not really concerned so much about these three things at the same time when we build systems, just about resources or just about some quality things. But I find that these three things are really key in the world of systems. Why is that important now for us? Because the claim here is that we always try to reach a certain equilibrium, an operational equilibrium, in this world of resource, quality, and cost, so that the system, the overall system performance, is in an equilibrium and not like this ship here tilting towards one side. So how do we do this actually? So when we look at system control-based service level objectives, which are just a measure for some form of a requirement, we translate them into SLOs. We kind of map them into measurable technical metrics. And they represent a form of a threshold for us, right? And that space that they determine is inside a hexahedron, inside this three-dimensional space. So now I'm trying to visualize it, so to speak, so that everybody can imagine it a little bit better. And the space is the constraint for the actual infrastructure inside this hexahedron. So the infrastructure then is represented as points, and it is of course not unlimited. Similar to the human body, we are not unlimited in our muscle growth, in the capability to run fast or to run long distance, etc. There are limits. And the valid configurations are always inside this hexahedron, inside this point space. And they are basically can be visualized by a blanket, by a stretch blanket. So this is an idea that I had initially, and I found by coincidence, more or less, that there is a way that this can be expressed mathematically, to my great joy, and that is by Markov blankets. It's a very simple idea developed by Pearl, the Turing Award winner. And he's basically saying that, okay, the Markov blanket of any random variable is a subset of the nodes that provide enough information to statistically infer the value. So you have a node n, and in any Bayesian network, the Markov blanket of this node n is composed of its parents p, the children c, and the co-parents of the children s. Very simple. So in other words, we just reduce everything around it and we say, okay, we just focus on the immediate actors that are influencing this. It's not really a magical thing, but this is actually constantly being applied to in us as well. And I later discovered that Markov blankets are all over the place in nature, which is a bit frightening. It's kind of a fractal thing that is occurring everywhere. And Pearl was suggesting to use then these Markov blankets as a tool for causality. So we filter by using these Markov blankets. And I thought this is a neat idea. Maybe it can be useful for our systems, because then we limit the information space. We don't need to constantly look at the whole system, right? So we try to apply these Markov blankets that can create then a formal boundary between system, external states, internal states, which is quite helpful because we have all these sensors, they provide data from the outside, and then we have to do some form of action based on this. And this is called in the literature causal inference. And Pearl was talking about causal inference in the terms of the ladder of causation. We can then learn about, observational causation, interventional, or counterfactual. And this helps us to explain why things are as they are, right? So now comes the first step of the contribution, so to speak, where we say, okay, we use the requirements in the expression, in the expressed form of a service level objective, and these SLOs can be seen as these nodes in a Markov blanket. So these SLOs are specifications that need to be ensured, right? In a system, you say the latency has to be lower than X. The bandwidth has to be Y. GPU needs to be this. Memory needs to be that, etc. So this is one first ingredient. The second technical term that we used is elasticity strategy. So I made you familiar with the term elasticity. Now, elasticity strategy is anything that we define that intervenes in something. It basically says something about add more resources or change the quality, for example, of the resolution of your camera and things like this, right? Every intervention is an elasticity strategy. And the other term which appears more frequently now these days is edge computing. Edge computers, which are nothing else than computing infrastructure which is closer to where the data is being produced. So here I'm just introducing a couple of these terms which are important. And the overall goal is, of course, that we can always fulfill the service level objectives by using the optimal resources that are at our hand. So if the problem is smaller in its requirement for resources, we don't need to go to the cloud. And frankly, also the applications themselves, they don't tolerate that anymore. We have a couple of application areas where you need to have extremely low latencies, and it is not possible to send stuff to the cloud and etc. and go back. So we then applied this idea of these SLOs in a hierarchical way, and we call them deep SLOs. At least this is the current state of the naming that we have. Not everybody is happy with this name. I personally like the name, but in any case. So the idea of this deep SLO is that we construct a hierarchical version of these SLOs and provide therefore a Markov blanket with this. And then we are allowing the aggregation towards higher abstractions and smaller and lower abstractions. And this is quite helpful because then we can, once we put these SLOs together, we can actually bring more semantics, more meaning into the relationships between these SLOs, which we typically currently don't have, because when we say latency is X, etc., we don't know really how it is related to some other aspects of the metrics. But it would be nice if we can build applications and reason about, okay, what would happen if I increase the bandwidth, for example, on this part of the system, or I put GPUs on that part of the system. We don't really can, with high confidence, say something here. So this allows us to build composable behavioral models and even include the edge infrastructure and provide more reasoning capabilities or causality-based statements about why things are as they are. So we have different concepts, for example, like you see here. Some are concerned with the behavior, some are concerned with the action space, what you can do, and some are influenced by external contextual factors that are influencing the overall system. So the deep SLO idea in an abstract way is that all SLOs are formulations of the relationships of metrics, of two or more metrics, and they determine an SLO, right? And or elasticity strategies are interventions saying something about what to do when the SLO cannot be fulfilled. They are on the sidelines here. And since they are hierarchically structured in a vertical way here, you can basically develop them by different people for different purposes. So the idea now is that these SLOs can be, when you look at highest abstraction levels, they can be seen as business SLOs, but the lowest abstractions are actually very close to actual development SLO activities. So it's quite different. And with these vertical relations, we can incorporate purpose. This is something, what I would claim is kind of a novel thing compared to the way we develop systems now. And we can even integrate transversal features such as privacy, security, energy efficiency, etc., which we cannot do typically when we build systems, as we build the systems nowadays. But the problem, of course, is I need to convince many people to have an SLO first approach to building systems, because this is not a normal thing to do. This is not how we build systems nowadays. And there are many scenarios. So Boris Sedlak from my group was working on stream processing scenarios, like for video processing or mobile mapping or QR scanners, where in case there were time-critical adaptations required, and he was using that mechanism that I was describing here to do that. And also dealing with problems which we call elastic quality. So for example, the problem is that we have limited resources, like with these edge devices, and we need to find alternative and effective strategies to ensure that the processing of SLOs actually works out. So here we have to use Markov blankets to create this interpretable representation of a service behavior. And there are many examples here. And Boris developed a three-step methodology to do that by providing Bayesian network learning, Markov blanket extraction, and then the actual inference that you see here represented. So this is how we do it. And we have done experiments where we try to generalize this approach, where we came up with transitive requirements to compose these Markov blankets of dependent services to find the implications and optimize these deployments. We try to span the computing continuum with these SLOs through microservices, and also do SLO-aware offloading of tasks to other devices that we have, typically in these autonomic vehicles scenarios. There are a lot of shortcomings which we deal with here. The typical Bayesian network learning requires large amounts of training data. It is computationally very expensive also. So more recently we started to look into these neuroscience approaches developed by Friston, which is based on these Markov blankets and this free energy principle. So it's a framework for understanding how humans learn, and we apply this to our world. And the idea, as I was alluding to now a couple of times, is to minimize the free energy. So it's a measurement of uncertainty. And the goal is always to maintain our homeostasis and to predict any changes in our environment, right? So the free energy principle is to try to minimize the difference between what we predict and actually what is. So I always bring this example when all of us, we have a certain worldview. And if suddenly an alien beams up here, we have to really seriously reconsider our worldview, because this is something that actually shouldn't be possible, right? So we have to definitely create a new model of our beliefs, right? And the mechanisms described in this active inference are dealing with perceptions, so involving the belief updates about the state of an environment based on these sensory inputs, about the action space, that what are the actions that I can actually do in order to minimize the free energy, and the learning aspects as well. So how can I adjust these parameters of these generative models? And the active inference then is this framework that integrates all of these aspects. And we have tried to implement this active inference framework as in the form of agents in all the different computing parts of the infrastructure. And this is quite amazing that we have shown in smaller examples now, but we are scaling them up in the future to show that it actually is feasible to do it. We don't need to the learning can be delegated to these forms. And as I was saying in the beginning, these Markov blankets, they occur everywhere in nature, from the small cells to bigger plant configurations, and even to societies. That is the way how we are organized in the smallest and also in the largest, which I find quite interesting. And we apply that now to these different cases. I don't want to go into too much detail here, but we apply them to the world of our typically smaller systems at this point, because we demonstrate that it is possible to encapsulate that. And we build the small case studies in the form of prototypes. And we show that it is very feasible to actually implement that. And we have done that in a number of papers, which are listed here, where we try to show that these active inference agents have a reasonable benefit compared to the way that we typically build the systems nowadays. So we are proponents of this equilibrium in the compute continuum through the active inference way to run things. And we created kind of a research line or a model how to actually go about this. So some parts I was talking about here, looking at these Markovian models, doing deep neural networks and agent-based more recently to actually implement those things. So to conclude this presentation, there were three things that I'm trying to pitch here to convince you. The first one is that we actually do have a distributed computing continuum, which is also maybe not everybody agrees. I'm saying that we should see those different parts not in isolation, but we should put them together so that we can have a better ability to reason about everything. The second is that based on this understanding that we are required to put intelligence into all aspects of this infrastructure, it is not enough to have a central coordinator of everything. Intelligence needs to be everywhere, equivalent to the body. Every information is in every cell. That's pretty interesting to consider, right? Everything in the body is organized like this. And the third question is basically some mechanisms. How can we do it? And here are some proposals that I introduced. So we introduced the concept of service level objectives being applied to the usage of Markov blankets and the usage of active inference versus traditional machine learning, which is, of course, quite different to this approach. So with that, I thank you very much for your attention, and we are ready for questions.
Do you have one microphone or you have more? I have another one. Thank you, Schahram, for giving us time for questions. That's what is always appreciated in keynotes, because, of course, the question time is frequently the most interesting part of any keynote. So please, I understand that many of you are eager to ask questions or make comments, express your own opinions. Am I right?
Oh,
yes, okay. Will he get the microphone?
Thank you very much. Thank you very much for a great talk. And I'm especially grateful for this interpretation related to Markov blankets. I do like Bayesian networks, or Bayesian belief networks, some people call them recently. Yeah. And I think that this idea of looking at complex systems, like these hierarchies in terms of Markov blankets and causal inference, is fantastic. And actually, I was wondering during your talk about maybe about some examples of the meaning of conditional independence in such structures, because in Bayesian networks you have this non-trivial relationship that if you have converging arrows, then some states are independent unless something happens in their common child. So I would like to ask you, maybe for your opinion about the following idea. Let's imagine that we are testing or fixing such systems. We have independent components. They are usually independent, so we can test them separately. But if something goes wrong somewhere on top of this hierarchy, then suddenly they become interconnected, and we have to test them together somehow. So yes. This is my question. Thank you very much.
That's a fantastic question. So I don't know if this is answering your question, but some intuition that we have developed in the past was that actually these Markov blankets, they are kind of moving entities in a sense, that they can be sliced and stitched in different shapes or forms. I don't know if this kind of addresses your point, but my feeling is that it could be one solution to this. So in other words, what we would try, and we will try to do, is to create new ways of stitching these Markov blankets together. And your question points to exactly those cases which determine how the shape of the Markov blanket should be. Yes. Yes. So this would be one approach to address this problem. We are not there yet, but from the visualization point of view, this idea of stitching these Markov blankets we already had this idea a couple of years ago, but we have not really fully materialized it yet, because we are now busy building the foundations and creating the simulation infrastructure for all of this to actually come to that interesting point that you are mentioning. Thanks very much for this question.
Are you happy, Dominic, with the answer? A fantastic question and a fantastic answer, right? Okay. Can I have more questions? Can we have more questions? Marcin? Okay.
Well, one of the things that happen in Edge Cloud Continuum today is introduction of more and more of green energy. Mm-hmm. And green energy itself introduces a lot of variability and unexpectability, because you may have a prediction it's gonna be a beautiful day, except that there is gonna be one big cloud. And if you are on a beach, then one big cloud comes, goes, you may feel a little bit shiver from the wind coming from the sea, but you're gonna be okay and it doesn't matter. However, if one big cloud goes over a photovoltaic farm, then there is an immediate and serious drop in produced electricity. And then there is the recovery, and the network network of energy is seriously disrupted, which means that if we talk about Edge Cloud Continuum, where we have devices that depend on this energy, there is overall the prediction it's gonna be a good day. So you put into your model, it's gonna be a good day, we can put the loads on those devices, and then suddenly it doesn't work. Yes. Is your model either now, or do you see how your approach can handle introduction of green and highly unstable energy resources into the ecosystems?
Well, from the principle standpoint, it is exactly what we are saying or claiming. This is the starting point. We need to become much more fine granular in order to be able to change the behavior of the different system parts, right? So what you're saying is actually the starting point for our motivation as well. One other principle I did not manage to talk about is what we called many years, I think more like 10 years ago, we called it osmotic computing. And the idea is here, similar to osmosis, where you see a molecules from high to low density movement, we want to apply the same principle in the world of the compute continuum. Here the idea is that we need to be able to shift computational workloads, which have been currently fixed, designed for some particular hardware, some particular configuration, and we need to be able, the infrastructure needs to be able to direct them and let them execute on a different infrastructure. And I think that this is exactly what you're pointing to. You're pointing to circumstances change. You had designed the system to be executed on platform A, but since there is, for example, in your case, there is no energy here, you need to shift the computation elsewhere, right? So that is from the principle, as far as I understand your question, exactly those cases where we would like to apply this principle. So that the continuum is much more flexible and not geared only towards one part.
Yeah, the continuum may be flexible, but the jobs, we are working with a cloud provider, and uploading a job takes uploading data to be able to execute the job takes 7 to 12 hours. Because this is, in our case, those can be images from satellites that are doing for geospatial tasks. And in this case, we are learning from the cloud provider that there is no way to move the job anywhere as soon as it's located somewhere. So I think that you need to very carefully express the class of jobs for which your approach will work, and where are the boundaries, not of the blanket, but of the class of jobs. Because if the job is just computation, no data, and the job itself is small, then you can move it fast around. But if there is a time of movement of jobs that needs to be included into the model, yes?
Yeah, this is certainly true. There are many jobs which require this heavy computational infrastructure, but there are also many other jobs that could be moved around and which are also not being moved around today. So it's both sides of the spectrum. Some are impossible, some are possible, and some are even more possible. So I think that we need to take care of all of this spectrum. And some will be probably not possible because you need to have cloud infrastructure, you have tons of data, and you can also investigate if there are other ways of computation, of learning that doesn't occur all on the cloud with massive data. So there are also other approaches to look into this, right? So also possible. Similar to the argument I was bringing, that also for the human body, we are actually, the most important part of our lives is what? Breathing, right? Try not to breathe for 10 minutes. So breathing is actually not a conscious activity of the brain. It's quite interesting. So evolution brought us to a place, probably before that, I don't know, but that it is not primarily driven by the brain activity to constantly think about breathing. Probably we would be dead by now, right? We might forget breathing. That would be really bad, right? So it is delegated to another part of the system. So importance and complexity are kind of interesting aspects to look into as well.
Thank you. More questions? Okay, hoping something from the side of the room. So please.
First of all, thanks for the amazing presentation. I very much appreciate when people don't chase LLM slop and stuff like that, so it's very refreshing. But a question I have, can you maybe go to the slide about the deep SLO where you had like this structure? Yeah, exactly. So does this like sort of consider that you want to have this bidirectional, let's say, information has to go from like, let's say, bottom to top, and you want to have like control mechanism?
Yes, it is bidirectional, of course. Here you just see a one-directional arrow. That's probably so. This is just saying that the abstraction detail changes here when you go down. It's becoming more detailed, and on the top is a highest level of abstraction. So, for example, if you are a business owner of a system of a smart city application, let's say, right, you are concerned about, let's say, you are just from the business side, you are concerned about energy consumption on the top level. You don't care about the latency, the memory usage, this camera at that junction, and all of these things. So you just want to look at it from the top level. But if you are an engineer working on the optimization of the AI algorithm on that particular junction of the cameras, you have to go downside here in the SLO4 and below, right? So the idea is here that typically today they are not connected at all, right? So everybody's just doing something, and then at the end, the business side of everything is basically a made-up Excel sheet. So this is something that we try to avoid, and by doing this deep structure of these SLOs, the claim here is that we are able to better forecast what are the things that are going to change if we manipulate some part in the bottom or some part on the requirement side on the top.
Can I follow up?
Continue.
Just one more, small, yeah.
Yes.
You talked about forecasting, but going also back to what a colleague was asking in terms of stitching of Markov blankets, are you trying to like compete with the, let's say, quality of the forecast, or don't you think it's more important that you do get, let's say, audibility or like explainability, and that you can sort of troubleshoot later on? And did I understand correctly, you could basically then, let's say we have now a functioning method to reconstruct the graphs, like globally you have like all those like Markov blankets, and would you then get, let's say, if you're just interested to see, okay, which provider fucked up, sorry for my language, at that high level, then you could do this at the top level, just reconstruct top level. But if you need engineers to really look at what went wrong at, let's say, service level, then you can go one step down. Okay, so I understood it correctly. Okay.
Yes, but I think that in the future, probably more distant future, we could also envisage a system which does it automatically. So not in the sense of explainability, so that we know who to blame, but also how to fix it automatically, so that it doesn't happen. That goes back to the point of anti-fragility, because if you think of these systems typically as anti-fragile, then they can actually select pathways to make the system anti-fragile. And that is a very interesting thought. So basically the system then selects certain infrastructure parts so that the overall system becomes better, versus just something which is maybe just cheaper as it is now. But I think we are pretty far away from that at this point, maybe another 10 years or so.
We can still afford one or two questions.
Sorry, only one.
Or lunch.
But now we stay with us also till the
Yes, I tell until
so
the end.
we'll have an opportunity to catch you and to ask you.
We just need to tie him and stay here because he has a tendency to wander off. So we're gonna change Schahram here so he will be available.
But still we have a minute, and I have one question as well, which I do not have to ask. Anybody wanted to ask? Yeah, no. Well, my question to you, Schahram, is related to, I wonder if your work, if you try to relate your work to this idea of holons.
Of what?
And holons and Arthur Kessler's work on holonic systems and holarchies and understanding complexity by really trying to understand how biological systems work, or is not your thing?
I came across it many years ago. I cannot recall it completely.
Okay.
I am more attracted to the work of Mike Levin now, for example, in the world of biology. I find it extremely interesting. But yes,
well,
probably it is related because I came across it, and
okay.
I think it's a couple
Arthur
of years.
Kessler. It was an Austrian,
Yes.
Hungarian
Yes.
guy, and
Yes.
he wrote he wrote various things, including something about complexity.
Yes.
But
yes.
we are talking 1956 or
Yes,
something.
exactly. It's a couple of months old, yes.
So we have a right not to remember. Okay, so this was my 5 cents of worth. I don't see anybody else jumping up with hands up, not giving up, but trying to ask a question. So listen, thank you very much.
Thank you.
Thank you, my friend.